Hello everyone, we're going to be solving a problem on moments about a point. This problem is going to be in 2D, and the main aim of this problem is to help us get acclimated with solving moments or computing moments about a point in 2D. And as we have seen in lecture, moment is nothing but the tendency of a force to rotate a body about a particular point or about a particular axis. Here is the problem for us today. So this is moments about a point in 2D. And the problem statement is as follows. So I have some kind of a rigid body. We will look at this as a cantilevered beam at some point in time. So we have a rigid body, and we have a system of forces acting on this rigid body. Okay, so here is a rigid body. It's fixed at one of the ends, and then it has the following shape. And then there are a system of forces which are acting on this rigid body. The forces are as drawn. There is a force of magnitude 250 newtons acting in the following manner. This we will call as F1. So F1 has a magnitude of 250 newtons, and it's at an angle of 60 degrees with respect to the vertical. So this angle here is 60 degrees. Then I have another force F2 which has a magnitude of 100 newtons acting vertically downwards. So this is F2 with a magnitude of 100 newtons. And then I have finally one more force which is acting at this particular point on the rigid body. This is having a magnitude of 350 newtons. F3 350 newtons. A nice slope triangle is given to us here. This is your standard 3, 4, 5 slope triangle. So this is 3, 4 and 5 right angle slope triangle. And then some distances are also given to us. The distance of the force F1 from the point O on the beam. So I'm going to mark the point O on the beam right here. At this point is the point O, and there are some distances given to us. These distances are going to be noted as follows. So the first one is from point O to the line of action of F1, and this is given to us as 1 meter. Then from where F1 is acting at the beam to the point where F2 is acting, the distance horizontally is given to us as 2 meters. The length of the inclined portion of the beam is 2 meters here, and the inclined portion is at an angle of 45 degrees to the vertical. So this is 45 degrees as well. Alright, and so the rigid body, I'm just going to draw it in slightly darker colors. So here is a rigid body with all these forces acting on the rigid body. There are 3 of them. And the problem is asking us to find the resultant moment about the point O. Alright, so the question, find the resultant moment about point O due to the system of forces shown. Alright, so here is a problem. This is the point O, which is at the fixed end of the beam. You can notice that the width of the beam is not given to us in this case. So which means if something is not given to us, then it is perhaps of very little consequence to the problem. There are 3 forces. Force F1, which has a magnitude of 250 newtons, acting at an angle of 60 degrees with respect to the vertical. Then I have the force F2, which itself is vertical. It has a magnitude of 100 newtons. And then I have a force F3 which has a magnitude of 350 newtons, and there is a slope triangle 3, 4 and 5 which is given to us here. Distances are 1 meter to the force F1, then 2 meters from the force F1 to the force F2, which means that F2 is at a distance of 3 meters from the point O. Then the inclined portion of the beam, the entire length is 2 meters, and the vertical line here makes an angle of 45 degrees with the inclined portion of the beam or the rigid body. And the aim is to find the resultant of all of these forces causing a moment about the point O. Alright. So here is what we're going to do. We're going to take a look at each of the forces. I'm going to take a look at the force F1 first, find the moment of this force about the point O. Then I'm going to find the moment of the force F2 about point O, and then we're going to find moment of the force F3 about point O. The resultant moment is going to be the vector sum of these individual moments about the point O due to the system of forces. Alright, so let's consider the force F1 first. I'm going to draw the rigid body once again as before in the previous page. It's fixed at one end. In this case, the inclined portion of the beam is inconsequential because the force F1 is acting on the straight portion of the beam. I have the force F1, which is given here. Now notice the point of application of the force. The point of application of the force is this point here on the beam, which means that if I break F1 into its components must also be acting at that particular point. So I'm going to break F1 into its components. These are the components, horizontal and then vertical. So there is this vertical component right there, and then I'm going to have a horizontal component which is drawn overlapping the beam itself. So you can see these two components. The angle is 60 degrees in there. This is the force F1, which has a magnitude of 250 newtons. Then I have distance from the point O, this is the point O, onto the line of action of the force here is going to be 1 meter horizontally. And this component here is going to be F1 times cosine of 60. This component here is F1 times sine of 60, which we can find out easily by completing the triangles. And so now all we have to do is find the moment of the force F1 cosine 60 about the point O, F1 sine 60 about the point O, and that will be the moment caused by the force F1 about the point O. Alright. So I'm going to write it in the following manner. Moment about the point O due to the force F1 is equal to the algebraic sum of the moments due to each of its individual components. Now watch this. If I look at F1 sine 60, you see that the line of action of F1 sine 60 is passing through the point of interest. If the line of action of a force passes through a point of interest or intersects the point of interest, then this force will not cause a moment about the point O, because there is no perpendicular distance whatsoever to speak of. Moment of a force is always a product of the magnitude of the force and the perpendicular distance from the point of interest to the line of action of the force. Right? So in this case, F1 sine 60 will not cause a moment. So this is going to be F1 sine 60 times 0, where 0 is the perpendicular distance written in the parenthesis here. And then I'm going to look at F1 cosine 60. F1 cosine 60, this is the line of action of F1 cosine 60. You see there is a line parallel to F1 cosine 60, and the distance between these two parallel lines, which is obviously going to be a perpendicular line, is 1 meter. Which means that the moment arm for F1 cosine 60 is 1 meter. And how do I find the moment? It's going to be the magnitude of the force times the perpendicular distance. So this is going to be F1 times cosine 60 times 1. But what is the sense of the moment? What is the direction of the moment? Right hand rule here. Fingers of my right hand aligned with the direction of the force, the line of action of the force. You see my palm is facing the point of interest. The point of interest is the point O. I take my fingers, I curl them, the direction of my thumb is going to give me the direction of the moment. It's in the positive Z direction if I call the direction out of the page as Z. But if I look at the sense of the moment, my fingers are curling in the counterclockwise sense, which means that this is going to be positive according to our sign convention. Right? And F1 is 250 newtons, cosine 60 is a half, so this is going to be 0 plus 250 times cosine 60 times the distance of 1, or the moment about the point O due to the force F1 is going to be 125 Newton meters. And look at the sense of the moment. This is going to be in the counterclockwise sense, right? Or this is going to be CCW. It is enough if we either draw this small circular arrow here or write CCW. My preference is to write CCW because that tells me that this is a positive moment, which means that I can as well write the answer as plus 125 Newton meters. So that's the moment about the point O due to the force F1. We have to do the same thing for the force F2 and for the force F3, and then we have to add them up algebraically. Alright, let's consider the force F2 now. F2 is a slightly easier customer because it does not have any components that you need to split it into. It is already vertical here. So here is the force F2. F2 has a magnitude of 100 newtons. I'm going to draw the rigid body first. So here is a rigid body. In this case as well, the oblique slanted portion of the rigid body does not have any role to play whatsoever, but it will become important in the next part of the problem when we handle F3. Now F2 is acting in the following manner. So this is the force F2, and then the point of interest for me is the point O, which is situated here. Then here is what I do. I draw a line parallel to the force F2, and this is the line of action of the force F2, and then I find out, okay, what is the distance of the force F2 to that particular parallel line, and that will give me my perpendicular moment arm, and this is going to be 1 plus 2 or 3 meters, because you would remember that F2 is at a distance of 2 meters from F1. F1 is at a distance of 1 meter from the point O, so the total distance is 3 meters. Alright, now moment about the point O due to the force F2. This is going to be the magnitude of the force times the perpendicular moment arm, which is going to be 3 meters. But the question is this positive or is this negative? And for that we need to use the right hand rule. And if I look at the right hand rule, here is the right hand rule. It's slightly harder to place my fingers this way, but I hope you get the idea. My fingers are pointed in the direction of the force F2. My palm is facing the point O. I curl my fingers. You see the direction of my thumb is into the board or into the page, and so this means that the force F2, if I look at this, the force F2 is trying to cause a rotation in the clockwise direction. Right, so this is going to be 100 times 3 or 300 Newton meters in the clockwise direction. So clockwise, or moment about the point O due to F2 is 100 times 3 in the clockwise, or this is going to be 300 Newton meters with a negative sign. You can write this as 300 Newton meters clockwise. If you write the clockwise, you don't need to put the negative sign. If you put the negative sign, you don't need to write that as clockwise. That's double counting it. Alright, once again, the fundamental idea being the moment about a point is the magnitude of the force times the perpendicular distance here between the line of action of the force and the point of interest. And then the sense of the moment is produced by using the right hand rule. You place the fingers of your right hand, align it with the direction of the force. Your palm has to face the point of interest. Look at the way the force is pointing, and then you look at the sense of rotation produced. It's going to be in the clockwise direction, or the clockwise sense. Alright, so we have the last one, which is the big guy, which is F3. F3 is slightly trickier because it has skewed components, and here is how we should be handling F3. So I first of all have the rigid body. So this is the force F3. I have the rigid body right here. So this is fixed, and then the rigid body is coming out. This is where the point on the body where the force F3 is acting. So here is the force F3. A slope triangle is given 3, 4 and 5. This is 3, this is 4, and this is 5. And so this is very important now. this is the point of application of the force F3, which means that its components must also originate from that particular point. Which means if I draw the components of F3, I'm going to have one in the horizontal direction, I'm going to have one in the vertical direction, and the component in the horizontal direction is going to be F3 times 4 by 5 using similar triangles, and this is going to be F3 times 3 by 5. Now we need some perpendicular distances, and so here comes the question of the 2 meters. So this distance here was 2 meters, and then the angle given was 45 degrees. So I'm going to break this into two pieces now. Look at this here. So this angle is 45 degrees, which means that this length is going to be 2 times sine 45, so many meters, and this height is going to be 2 times cosine 45, so many meters, and we already know this distance here was 3 meters to begin with. Alright, so we have all the distances, 3 meters from the point of application of the force, including the 2 cosine 45 and 2 sine 45, 3 meters from the point of interest to this particular point on the horizontal portion of the beam or the body, and then I have the slanted portion here broken into two pieces in terms of its length, 2 cosine 45, 2 sine 45. I have the force F3 broken into two components. I make use of the similar triangle idea here by seeing this slope triangle, and then I have F3 times 4/5 in the horizontal, F3 times 3/5 along the vertical. These are the components of F3. Alright, so now we need to compute the moment about the point O due to the force F3. I start off by looking at the horizontal component of the force. Look at the horizontal component of the force, it's F3 times 4/5, so the magnitude is going to be F3 times 4/5. And then the perpendicular moment arm for this force, watch this, I'm going to extend a line parallel to the line of action of the force from here, passing through the point O. I'm going to extend the line of action of this force here as well, and you see that this entire distance is going to be the moment arm for F3 times 4 by 5, so which was 2 times cosine 45 as we already had it, so 2 times cosine 45. What is the sense of the moment? Right hand rule once again, fingers of my right hand aligned with the force F3 4/5, and then I have my palm facing the point of interest. Watch that, it's facing the point of interest. I curl my fingers curl in the counterclockwise direction, and my thumb is going to come out of the board, and so this is going to be a positive sign because it's counterclockwise. And then I do the same thing for F3 times 3/5. So F3 times 3/5 is this particular force here. I'm going to extend its line of action passing through here, and I see that this distance here, which we calculated below, is 2 sine 45, so many meters, and so I have the force F3 times 3/5 times the perpendicular moment arm. You see, all the way from the point O to the line of action of the force F3 times 3/5, the moment arm is 3 meters plus 2 sine 45. So this is going to be 3 plus 2 sine of 45. And then what is the sense of the moment? Right hand rule once again, fingers of my right hand aligned with the direction of the force F3 times 3/5. My palm, you see, is facing the point O. I curl my fingers, it's in the counterclockwise sense, which means that I'm going to get a positive moment here. And all I have to do is start substituting. F3 had a magnitude of 350 newtons, so this is going to be 350 times 4/5 times the moment arm was 2 times cosine 45, positive, and then I have the other component positive as well, 3/5 times 350 times 3 plus 2 sine 45. Right, so that's going to be 3 plus 2 by root 2, and if I add these up, I'm going to get the following. Moment about O due to F3 is positive because both these components are positive. I get a positive value, and this is approximately 1323 Newton meters, or you can write this as 1323 Newton meters in the counterclockwise sense. So this was the slightly harder of the three forces. The force is given at an angle. We have to take this angle and then break it into its components here. I make use of the idea of the slope triangle given here and similar triangles which we've been doing for quite some time now. Then I say that okay, this is f3 times 4/5, that's f3 times 3/5. f3 times 4/5 perpendicular distance to the point O is 2 cosine 45. f3 times 3/5 perpendicular distance is 3 plus 2 sine 45, as you can see here. Sense of the moment, this is the force, point of interest is there, so this force is going to cause a rotation in the counterclockwise sense. This is the force, point of interest here, this is also going to cause a rotation in the counterclockwise sense, or the counterclockwise direction. So we have all the forces causing moments, we have calculated all these values. All we have to do is algebraically add them up. So I'm going to summarize this in the following sheet, all the values that we have so far. Moment about O due to the force F1. We found this to be plus 125 Newton meters. Moment about O due to the force F2 was minus 300 Newton meters, and moment about O due to the force F3 was plus 1323 Newton meters, where our sign convention is clockwise is negative, counterclockwise is positive. This is our sign convention. Alright, so the resultant moment about O resultant is the algebraic sum of these quantities, moment about O due to F1, moment about O due to F2, moment about O due to F3, or this is 125 minus 300 plus 1323, and the total result is going to be 1148 Newton meters with a positive sign, which means that moment about O due to R is plus 1148 Newton meters, or 1148 Newton meters CCW. Now one last thing before we quit on this problem is to write the force or write the moment as a vector, because moment is a vector, it has a sense, it has a direction, it has a magnitude. The sense is given as either clockwise or counterclockwise, the magnitude is 1148, and then the direction is either into the board or out of the board, or into the page or out of the page. And so here is how you want to write that. So I redraw my system here. I choose a positive x and a positive y coordinate system. So first of all, I see that here was the problem given to me, and there were several forces acting. There was a force acting here, there was a force acting here, and then there was a force acting here. The first thing I do is I set up a coordinate system where I say, okay, on the plane of the paper I have my positive x, I have my positive y, this is positive, and I'm going to say that counterclockwise is positive, which means the direction that is coming out of the page, which is the z direction which is coming out of the board or out of the page. The z is going to be the direction of the rotation. So all my rotations, if I consider a problem in planar statics or dynamics, even if we go there, these rotations will always be either into the board or out of the board. Alright, so planar rotations, planar moments, which means moments in 2D will have directions either into or out of the plane of the paper. Right, so either the rotations will be out of the plane or it will be into the plane. And for our problem, we had MO resultant was plus 1148 Newton meters, which means that this was a counterclockwise result. And so if I now call unit vectors, along the x-axis is I, along the y-axis is j, and along the z-axis is little k, I see that if I have a counterclockwise sense, if my fingers are curling in the counterclockwise sense, then my thumb is going to be coming out of the board, which means that the direction of the resultant moment is 1148 Newton meters in the z direction, positive z direction, and the unit vector there is plus k, which means that if I have to write this as a vector, then this is going to be 1148 K Newton meters. And key point, if you look at planar moments in 2D, these will either have a direction into the plane of the paper or out of the plane of the paper, or plus or minus z direction. Plus or minus z direction. Thank you.